neutron stars. You've probably heard the term thrown around, maybe in a sci-fi movie or a headline, but what? Are they really? Well, it turns out there's some of the most extreme, most bizarre, and most important objects in the entire universe. So today we're going to go on a little journey, a cosmic detective story, if you will, to uncover how we went from just a wild prediction on paper to actually finding these incredible stellar ghosts. Let's dive in.
You know, our story doesn't start with a telescope, but with a piece of paper. Way back in 1932, long before we had any way of finding one, a physicist named Lev Landau started speculating about a star made entirely of neutrons. The physics he was working on pointed to an object so dense, so strange, that he gave it this perfectly eerie name, Unheimliche Sterne, which is German for weird stars. And honestly, he wasn't wrong.
So here's how we'll crack this case. We're going to do it in 4 parts. First, we'll look at the ghostly prediction that kind of haunted physics for decades. Then we'll investigate the first bizarre clue, a clue that had astronomers seriously scratching their heads. After that, we'll decode that clue and reveal a kind of cosmic lighthouse. And finally, we'll see how these things became the most extreme laboratories in the known universe.
All right, so for the first part of our story, we're dealing with a theoretical ghost. I mean, for nearly 40 years, neutron stars weren't something you could point a telescope at. They were just there, living in the equations and the daydreams of theoretical physicists.
Now, what's really wild about this timeline is just how long the wait was. The idea pops up in 32. By 39, guys like Oppenheimer had even calculated what their basic structures should be. But then, radio silence. For almost 30 years, this amazing prediction was just a theory, a ghost in the machine, just waiting for someone to accidentally stumble upon it and bring it into the real world.
So why were physicists so sure these things had to exist in the first place? Well, it all comes down to this, the Chandrasekhar limit. Think of it as a fundamental rule for dying stars. If a star is below about 1.4 times the mass of our Sun, it gets to retire peacefully as a stable white dwarf. But what if it's heavier? Gravity wins. The collapse doesn't stop. This limit wasn't just a suggestion. It was a physical law that screamed, something else must happen. It's the reason neutron stars had to be real.
Okay, let's get to our second act, because this is where the story takes a really unexpected turn. After decades of theory, the first clue didn't come from some famous astronomer actively hunting for a neutron star. Nope, it came from a graduate student who found a signal so weird, so artificial sounding, that the first suspects weren't stars at all, but little green.
I mean, try to put yourself in Jocelyn Bell's shoes. You're just trying to get through your PhD, scanning the skies, and suddenly you find this, a pulse. And not just any pulse, but one that repeated with a precision that was, frankly, unnatural. It was more accurate than any clock on Earth at the time. Nothing in nature was supposed to be that perfect.
The signal was so clock-like, so manufactured seeming, that the team half-jokingly nicknamed it LGM-1 for Little Green Man 1. And for a little while there, it wasn't entirely a joke. They had to genuinely consider the possibility that they'd found a beacon from an alien civilization. It was only when a second and then a third similar signal was found in a totally different part of the sky that they realized, okay, it's not aliens. It's a whole new type of star.
And this brings us to part 3, the actual detective work.
So we've got this strange pulsing signal, and we've got this decades-old theory about an incredibly dense, compact star. The challenge now was to prove, beyond a shadow of a doubt, that these two things were actually the same thing.
So the leading theory that emerged was the rotation-powered pulsar model. The idea is basically a cosmic lighthouse. You have this tiny, super-dense neutron star spinning insanely fast, and it's got a ridiculously powerful magnetic field. This field shoots out beams of radiation from its poles. And if one of those beams happens to sweep past Earth as the star rotates, bleep, we see a pulse. But here's the brilliant part. This model made a critical, testable prediction. If the energy for that beam is coming from the star's spin, then the star has to be slowing down over time, even if it's just by a tiny amount.
And this is the awesome tool astronomers use to track their suspects. It's called a PP dot diagram. Now, it looks a little complicated, but think of it like a detective's evidence board for pulsars. How far it is to the left or right tells you its spin speed, and how high up it is tells you how fast it's slowing down. Just by plotting a single dot on this chart for any given pulsar, astronomers can figure out a ton of stuff, like its age and how strong its magnetic field is. It's super clever.
But remember, this was still just a really good model. It fit all the data, but there was no direct proof. I mean, how on earth could you measure the magnetic field of something trillions of miles away and prove it was as powerful as the theory said it had to be? They needed a smoking gun.
And here it is. This graph, which came from an experiment on a high-altitude balloon in 1976, was the final piece of the puzzle. What you're looking at is the light from an object called Hercules X1, broken down by energy. And you see that clear dip and then a bump in the data? That's not just random noise. That is the exact, unmistakable fingerprint that matter leaves behind when it's being violently whipped around by a monster magnetic field. This was it, the smoking gun.
The measurement they got was about 4 trillion Gauss. Okay, to put that into perspective, that's hundreds of millions of times stronger than the most powerful magnets we have ever built here on Earth. The theoretical ghost was real, and it was even more extreme than most people had dared to imagine. Landau's weird star had officially been found.
So case closed, right? Well, with their identity confirmed, neutron stars sort of changed jobs in the eyes of scientists. They were no longer just a cosmic mystery to be solved. They became a tool for solving other mysteries. They became laboratories for exploring physics at its absolute breaking point limits.
See, inside a neutron star, matter is crushed to densities that are just impossible to create here on Earth. We're talking a single teaspoon of this stuff weighing billions of tons. So by studying them, we get to probe the fundamental laws of nature under conditions that we could never, ever hope to build in a lab.
But that doesn't mean all the mysteries are solved. Big questions are still out there. For instance, we know pulsars are cosmic lighthouses, but we're still debating where exactly the light bulb is. The evidence points to two main suspects: the polar cap model, you see on the left, which says the light comes from right near the star's surface, and the outer cap model, on the right, which thinks it's generated much farther out in the magnetic field.
So really, the whole debate just boils down to location, location, location. Is the cosmic lighthouse bulb right on the surface of the star, or is it way out at the very edge of its magnetic influence? And figuring this out is really key, because it tells us about the fundamental physics of how these enormous magnetic fields actually generate all that energy we see. Another really deep mystery is what's going on deep inside the star's core. Obviously, we can't drill into one, but we can do the next best thing. We can take its temperature. This chart shows a bunch of theoretical cooling curves. A neutron star is born unbelievably hot, and then it cools down over millions of years. But how fast it cools depends entirely on the exotic, weird physics happening in its core. By measuring the temperatures of lots of neutron stars of different ages, we can start to figure out which of these theoretical curves is the right one. And that tells us about matter at densities we can't see anywhere else. And our ability to do all this detective work is just getting better and better. Just look at the difference here. On the left, that's the Crab Nebula as seen by an older satellite. And on the right, that's the same object as seen by the more modern Chandra X-ray Observatory. The leap in just how clearly we can see what's going on is, well, it's staggering. We can see details that were totally invisible before.
And this quote really just sums it all up perfectly. They went from being a weird star on paper to a cosmic lighthouse, and now to an absolutely essential laboratory for fundamental physics. The journey to understand the neutron star is one of the great detective stories of modern science, and believe me, it is far from over.
Which, of course, leaves us with one last tantalizing question. The clues we've gathered so far have completely reshaped our picture of the universe. But what breakthroughs, what new fundamental laws of physics are still locked away, just waiting for us to find them, deep inside the unimaginable crush of these collapsed stellar cores?